In this video, we're going to talk about quadratic functions. So we've already worked with quadratic functions. So again, this is sort of stuff we did before, but with a different name. Okay, so we're now calling it a function. So to define a quadratic function is a function of the form y, or f of x, I guess I should use. F of x is equal to ax squared plus bx plus c. Okay, so notice that the highest power here, so it's powers of x, and the highest power is 2. Okay, and here I guess a should not be 0, so that stays. So that is what a quadratic function looks like. And you probably recognize that this looks like the equation for a quadratic equation. So the graph of the quadratic is one that we've worked with heavily. It's called a parabola. Okay. And it's like the standard one is the y equals x squared. Okay, now if you look at f of x is a, so now we're just looking here. So this is consider when b equals 0 and c is also 0. Okay, when b and c are both 0, then we just have the form ax squared. And that's what the graphs look like. So notice if you have a equals 2, it's a vertically stretched version of the y equals x squared graph. Okay, if a is 1/2, then it's been vertically compressed. If a is negative 1/2, then it's flipped and vertically compressed. Okay, and negative 2 flipped over the x-axis and vertically stretched. Okay, so now notice when in the two cases over here, when it was positive, the parabola opened facing up. Okay, but when the a value was negative, the parabola opened facing down. Okay, so this is actually always happens. So if a is positive, the parabola opens up, and when a is negative, the parabola opens down. Okay, now we talk about this special point on the parabola. It's called the vertex. Okay, so this is the lowest or highest point of a parabola. Okay, that's what we call the vertex. Okay, so on these graphs above, the vertex never actually moved. Okay, so in all of them, the vertex would be at 0, 0. Now the vertical line that goes through the vertex is called the axis of symmetry. Okay, so that's the graph is symmetric about that line. Okay, so if we go the vertical line that goes through, you'll see that the graph looks the same on both sides. Okay, so it's symmetrical about that line. These aren't great examples because the line is the y-axis, but it doesn't have to be. Okay, so if the parabola is shifted horizontally, then this line will move as well. Okay, so there's two main methods for graphing quadratic functions. Okay, one is what we did in chapter 3, using transformations. Oops. Okay, so if we use transformations, we're transforming the graph y equals x squared. Another method is that we could use the vertex, the intercepts, and the axis of symmetry. So this is basically plotting some points of our graph. Okay, so let's do one using transformations. So if we're going to use transformations, then we need it to be in this form. Okay, so we need to be able to see how it's been shifted. Okay, so if we see it in the regular form, ax squared plus bx plus c, this doesn't tell us how the x squared graph has been moved. So we need to put it in this form, and to do that, we need to complete the square. Okay, so that's the idea. So let's do an example. Okay, so here my equation is 3x squared plus 6x. So what I want to do, I'm going to first factor out the 3. Okay, so then I have x squared plus 2x. And now I want to complete the square inside the brackets here. So because it's 2, I'm going to have to add 2 over 1 all squared. So that's 1 squared. So I have to add 1, which means I also have to subtract 1 so that I don't change the equation. Okay, now these first 3 terms give me a perfect square. So this is actually x plus 1 all squared. And then I still have that minus 1 left over. So then if I put the 3 through the equation in the transformed standard form, I think is what they call it, is going to be 3 times x plus 1 all squared minus 3. Okay, so that's our transformed graph. And maybe you want to write it as 3 times x minus negative 1. Okay, so that's the equation written so we can see the transformations. Okay, so this minus 1, or plus 1 if you want, this is going to shift. So maybe let's write what transformations we have. So we're going to have to shift left 1 unit. We're going to have to vertically expand by 3. Okay, that's from this 3 here. Okay, and then we're also going to have to shift down by 3 because of the minus 3. By 3. So those are all the transformations we're going to have to do. So let's do them. We're going to do them one at a time. So let's start with our initial graph, y equals x squared. Okay, so that looks like that. Okay, and then we're going to go this way, and we're going to do, we always do the horizontal ones first. Okay, so here's where we shift left, okay, 1 unit. So if you want to color the dots, okay, 0, 0 is going to go to negative 1, 0. Okay, 1, 1 is going to go to 0, 1. So what I'm doing is we subtract 1 from each x value. So actually, maybe I'm going to write that the way I did last time. So that's going to be x is actually being replaced with x minus 1. Okay. Orange dot. So this one's going to be at negative 2, 1. And this 2, 4 dot is now going to be at 1, 4. Okay, and this last one is going to be at negative 3, 4. So then I'm going to have my parabola that's just been shifted over by 1. Okay, so that's my new one. Now I'm going to go over here, and we're going to do the 3, the multiply by 3. So here I want to graph 3 times the graph we just had. Okay, so here we are vertically expand by 3. So that means y gets replaced with 3 times y. Okay, so our blue, so the negative 1, 0 stays at negative 1, 0 because when I times the y value by 3, I still get 0. Okay, the pink one now, instead of being at 0, 1, is at 0, 3. Okay, the orange one's going to be at negative 2, 3. And the other ones are going to be actually off the grid because they're going to be at 12 high. So the y value is going to be 12 there. Okay, so they're way too high to plot. So this is going to be really, really steep and narrow. Okay, so that's our new one. And now we just have to subtract the 3. So this is our final version. Okay, so here we are shift down 3. So that means our y value is going to be replaced with y minus 3. Okay, so negative 1, 0 is now going to be at negative 1, negative 3. Okay, negative 2, 3 is going to be at negative 2, 0. 0, 3 is actually going to be at 0, 0. And the other ones are still going to be at 9, so they're still too high to plot here. So it's just the same graph as we just had, but shifted down by 3. Okay, so that's our final graph. This should be a bit rounded, but okay, so that's what we look like. So you need to complete the square so it's in the form that you can see the transformations. So maybe let's just write up here. Okay, so this is y equals x squared with, so it's been shifted h units right. Okay, vertically expanded by a, and then shifted up by k units. Okay, so that's what's going on if it's in that form. Okay, so if we write it in that form, those are the operations you want to do, and actually in that order. Okay, so you can also find the vertex other ways. So if you have ax squared plus bx plus c, so you have it in the regular form, then we can tell that the vertex is actually going to be at negative b over 2a. That's the x value, and the y value is just the what it's evaluated at. Okay, so this is the x value of your vertex and the y value. Okay, so if your vertex is at negative b over 2a for the x value, then the axis of symmetry is going to go through that x value. So it's going to be at x equals negative b over 2a. Now, the way that you can see this, because this seems like it came out of thin air, so if we had it, if you find the x-intercepts, okay, so that's when you want to solve 0 equals ax squared plus bx plus c. The quadratic formula tells us that x should be negative b plus or minus the square root of b squared minus 4ac all over 2a. Okay, now this we could simplify as negative b over 2a plus or minus the square root. Okay, now because of the symmetry, because the symmetry goes through the vertex, the x values, the x-intercepts, sorry, should be equally distant, equally far away from the axis of symmetry. So that means that this is how they separate. So that means that this part here has to be the x value of, it has to be the axis of symmetry. So that means that the vertex has to be at that x value. Okay, so you don't need to remember that, but that's where it comes from. Okay, so now if we try to, so I was gonna, let's go back up here actually. So just to check, let's do this in a different color. Okay, so check down there. So if we look at this, okay, this is the axis of symmetry here. okay, and it's at x equals -1, right? So now let's just check, what is negative b over 2a? If we look at our original function in the form, a is 3 and b is, so a equals 3, b equals 6, and c equals 0. Okay, so this is going to be -6 over 2 times 3. So that's -6 over 6, which is -1. Okay, so that does check out for the symmetry. And the vertex is also at that x value. Okay, and then the y value of the vertex is going to be f of -1. So that's going to be 3 times -1 squared plus 6 times -1. Okay, so that's 3 minus 6, which is -3. So that means the axis of symmetry is x equals -1, and the vertex is at -1, -3. So we got the exact same thing we got from the transformations using the formula down here. Okay, now the reason I talked about that there is because I'm going to skip example 2 and leave that for you to try. So you can use the formula if you want, so you don't have to complete the square. Although if you do, you can actually see the vertex. So actually it says it right down here. So if you put it in this right form, then the vertex is given right away. Okay, so then your vertex is hk when it's in that form. Okay, so if we go back up and look when we put it in that form, okay, so our vertex has x value -1 and y value -3. So we could read it right from there. We didn't actually have to do all the transformations. So you can see the vertex right away. But anyway, you're welcome to use the formula here for example 2. So this is what I mentioned earlier. So if the parabola has 2 x-intercepts, then the x-coordinate of the vertex should be right in the middle of them. Okay, so that's because of where the axis of symmetry is. Okay, and that's why it's at -b over 2a, and that comes from the quadratic formula. Now, if you're given the vertex and one other point, then we can find the equation and therefore the graph of the function. Excuse me. So let's do an example like that. So we want to find the equation of the quadratic function where the vertex is 2, 1, and we have the y-intercept as 0, 5. Okay, so the fact that the vertex is 2, 1 means that our function has to look like a times x minus 2 plus 1, right? So this is in the standard form. So here the h is 2 and the k is 1. Okay, so this 2 is what goes there. It's the x value. And the 1 is what goes there. Okay, so that's the h and the k value if you look at the standard form. Okay, so using this form here. So I know h and I know k because that's the vertex, the x coordinate and the y coordinate of the vertex. So now what I want to do is use the extra point to figure out what a is. Okay, so now we use the point 0, 5 to determine a. Okay, so this point should satisfy the equation. So if I plug in 0 for x and 5 for y, the equation should be true. So that means that 5 is equal to a times 0 minus 2, oops, I should have a square up here, squared, plus 1. So let's subtract 1 on both sides. So that's going to give me 4 is equal to -2 squared a. So that's also 4. So 4 equals 4a, which means that a actually has to be 1 here. Okay, so that means our equation must be f of x is equal to x minus 2 squared minus 1, plus 1, sorry. Okay, so that's our equation. Okay, so some special features about our parabolas. So if you're in this regular form, ax squared plus bx plus c, the parabolas always have either a minimum or a maximum, right? Because they either open up or they open down. Okay, so if a is bigger than 0, so remember that means that it opens up. Okay, so it's going to look like, I don't know, something like this. Okay, that means that the vertex here is going to be a minimum. Okay, it's a relative minimum for the parabola. Okay, so the minimums are always the y values. So that means that the y value of the vertex is f of the x value. Okay, so that means that that's going to be the minimum value of the function. So remember this, the vertex here has coordinates negative b over 2a and f of that value. Okay, so similarly, if a is negative, okay, so that means that it opens down. Okay, if a is negative, that means that the vertex is going to be a maximum. Okay, so that means that f of negative b over 2a is the maximum value for the function. Okay, so just to remember, this is the y value of the vertex, which occurs when x equals negative b over 2a. So that's why we want to plug that into the equation. And then I'm going to skip this last example so you can just use that idea to tell if it is minimum or maximum and find the minimum or maximum value. Okay, so that's a little bit about quadratic functions.